Hello, calculus fans! Let's talk about equations of lines and planes. You're used to dealing with equations of lines in two-dimensional analytic geometry, and it's a very straightforward thing to deal with. You have to have a point and a slope, and if you have the point and the slope, then you can write down an equation of the line. That slope can be thought of as the direction of the line, or you can have angle of inclination. Any of those things are ways that you can describe the direction of the line. Once you have all that information, you can use the point-slope form to write down an equation of a line. Now, a line in three-dimensional space can be described by starting with a point on the line and the direction of the line. Now, we can describe the direction of a line using a vector. So let's let V be a vector that's parallel to the line, and let's let P of xyz be an arbitrary point on the line, and then we'll let r0 and r be the position vectors of p0 and p, respectively. So p0 is a fixed point, that makes r0 a fixed vector. P is an arbitrary point on the line and can vary, so r now is an arbitrary vector pointing to some point on the line. So that is, r0 is going to be the vector O P0, r is going to be the vector OP, and here we're describing O as the origin. Now let's let A be the vector P0, P. Let's show a picture of what's going on. So V is the direction vector of the line. It's pointing in some direction that's parallel to the line. O is the origin. R0 is a vector that points to some fixed point that we know on the line. So that red vector is not going to move. R is going to be a variable vector that can move around, pointing to some arbitrary point on the line. Now our vector addition rules will tell us that R is equal to R0 plus A. And bear in mind that A and the vector V are parallel. That means there's some scalar t such that A is equal to t times V. We're going to assume that V is a non-zero vector. Therefore, we can say now that R is equal to R0 plus t times V. This is what's known as a vector equation of the line. So every time you pick a value for t, that's going to give you a position vector for a different point on the line. So R0 is a vector pointing to a starting point. V is what's known as a direction vector for the line. So every time t varies, you get a line that's traced out by the tip of the vector r. So here's another picture showing us various values of t giving us different points on the line. As t becomes large positive numbers, we sort of move off to the right. T equals 0 points to the fixed vector that we're starting with, R0. Negative values of t move us off to the left side of the line. Now let's go ahead and write our direction vector in component form as ABC. So t times the vector v is ta, tb, tc. Now we'll also write r as an arbitrary vector xyz, and r0 is equal to x0, y0, z0. So bear in mind that ABC is fixed, r0 is fixed, the other values can vary. So our vector equation becomes xyz is equal to x0 plus ta, y0 plus tb, z0 plus tc. So we're just plugging everything in. And if we just equate the components, we get these scalar equations. Now remember that t is any real number. So those equations that we just wrote down, those are called the parametric equations of the line L through the point P0, and parallel to the direction V, which is the vector ABC. And every time you pick a different parameter value t, you get a different point on the line. So we're going to want to be able to use both a vector equation and parametric equations to describe a line. Okay, that's all for now.